I welcome you all for this third lecture on the topic of gas turbine. In the previous lecture, we started with the methods which can be utilized for the improvement of the performance or the thermal efficiency of the open cycle gas turbine power plant. And we have mentioned the three different arrangements, the methods, namely intercooling, reheating, and the regeneration. This is what the arrangement that we discussed for the intercooling. The arrangement for the intercooling that is normally used to reduce the work which is required for the compression of the air, especially when the pressure ratio is very high, and instead of compressing the air from initial to the final pressure, we compress the air in multi-stage compression process. So as such, in this arrangement the two compressors were shown, and the intercooler that is placed between the low pressure compressor and the high pressure compressor. This arrangement is helpful for substantially reducing the work required for the compression. Thus, this arrangement that helps to improve the thermal efficiency of the simple open cycle gas turbine power plant. This was the representation on the PV diagram, the shaded portion that represent the saving in the work which is done in the compressor by compressing the air in two different compressors, multi-staging compressors, and the temperature entropy diagram that is shown in the adjacent arrangement. The equation that is used to calculate the thermal efficiency by the intercooling arrangement, so that is given by the equation which is mentioned at the bottom of this slide. We will now proceed for the second arrangement that can be utilized to improve the performance of a gas turbine cycle. So that arrangement is known as the reheat gas turbine cycle. So as the name itself indicates, reheating, it means that you are heating it again. So what you are heating again in this arrangement? So let us see that. We are quite aware that the output of the gas turbine that can be considerably improved by expanding the gases in the two stages, and we can place a reheater in between the two gas turbines. Okay. The block diagram for the reheat gas turbine cycle that can be seen in this arrangement. We are having one compressor, we are having a combustion chamber, that is a CC, HPT that stands for the high pressure turbine. Then we are having the RCC, so that is nothing but the reheat combustion chamber, or we can say it is a reheater. LPT, so that is nothing but the low pressure turbine. In the intercooling arrangement, we have seen that we place the intercooler heat exchanger between the two compressors. Now what we are doing here, we are placing an additional reheater between the two different stages of the turbine, high pressure turbine and the low pressure turbine. The high pressure turbine, the power which is obtained from the high pressure turbine, so that will be used for the operation of not only the compressor, the low pressure turbine also provide the useful power output, isn't it? So the this arrangement for the gas turbine cycle, so that may not affect the work required for the compression, but it definitely increases the output which can be obtained in the gas turbine cycle. Okay, so we can see the different state points. Point 1, that is nothing but the inlet condition of the atmospheric air, ambient air entering into the compressor. State point 2 represent the condition of the air leaving the compressor at high pressure, high temperature. 2 to 3, so that is nothing but the heat which will be added in the combustion chamber. Condition 3 represents the state of the gases which are leaving the combustion chamber or that enters into the high pressure turbine. Condition 4, that represents the state of the gases after the expansion in the high pressure turbine to some intermediate pressure, and the gases which are leaving the high pressure turbine and before they are admitted into the low pressure turbine, they are reheated in this RCC, so that is nothing but the reheat combustion chamber, right? And condition 5, that represents the state of the air which is leaving the reheater or entering into the low pressure turbine. The state point 6, that is nothing but the condition of the gases which are left to the surrounding after utilizing their energy. And all these three components, that is a compressor, high pressure turbine as well as the low pressure turbine, they are mounted on the single shaft, the horizontal shaft that can be seen, and the generator that is mounted at the other end of this arrangement. The various state points that we have seen in the previous block diagram, so they can be represented on the temperature entropy diagram. The process 1 to 2, okay, 1 to 2, that is a compression, and thermodynamically speaking, this compression process is again nothing but an asentropic compression process. Okay, so we can see from the temperature entropy diagram, the process 1 to 2, so that entropy remains constant. So we can have here S1 that is equal to S2, entropy at point 1 that is equal to entropy at point 2, an asentropic compression process. The process 2 to 3, so that occurs in the combustion chamber. Okay, so that is nothing but the heating process as such, or the heat which is supplied during the process 2 to 3. So similarly, the heat added in this gas turbine cycle or in this reheat cycle, so that is also a isobaric process, a constant pressure heat addition. 2 to 3 is the constant pressure heat addition process. The process 3-4, so that process takes place in the high pressure turbine. Okay, so that is expansion process. One can also observe here that the process 3-4 is also a asentropic process, isn't it? So process 3-4 is nothing but the asentropic expansion of the gases in the high pressure turbine, right? Process 4 to 5, okay, process 4 to 5, so that is nothing but a reheater arrangement. Okay, reheat combustion chamber we can say. So it means that the gases after the expansion from the low pressure, from the high pressure turbine, and before they enter into the low pressure turbine, they are reheated. Okay, so 4 to 5 process, this one 4 to 5, so that is again nothing but a constant pressure heat addition process in the reheater, right? Coming to the last process, process 5 to 6, so that occurs in the turbine, so that is nothing but a low pressure turbine, and the gases are expanded from condition 5 to the condition 6. So this process is also indeed an asentropic expansion process in the low pressure turbine. Okay, so I repeat the processes, the sequence of the processes which takes place in this reheat cycle. Process 1 to 2, so that is the asentropic compression of the air in the compressor. The process 2-3, the heat addition at constant pressure in the combustion chamber. Process 3-4, asentropic expansion of the gases in the high pressure turbine. Process 4-5, reheating of the gases leaving the high pressure turbine and entering the low pressure turbine. Process 5-6, so that is nothing but the expansion of the gases in the low pressure turbine. Okay, now applying the energy balance and further simplifying the thermodynamic analysis, we can obtain the equation for the thermal efficiency of this reheat arrangement. So this thermal efficiency, we know that we generically give the definition for the thermal efficiency as the net work which is obtained from the cycle and divided by the heat which is supplied for the cycle. Okay, so output upon the input. So output is nothing but the net work. Input is nothing but the heat which is supplied during the constant pressure processes. So if we say there in the numerator, so we are having the WHP and WLP. So this WHP is nothing but the work which is obtained from the high pressure turbine, and WLP, so that is nothing but the work which is obtained in the low pressure turbine. The work is obtained from the high pressure turbine during the process 3-4. The work is obtained from the low pressure turbine from the process 5 to 6. Okay, so this is nothing but a total turbine work, WHP plus WLP. And to get the W net, we subtract the work which is required for the compression. Okay, so that is WHP plus WLP minus the work of compressor. Okay, so this is nothing but your net work, and divided by the heat supplied. So we are quite aware that the heat is supplied here during the two different processes, isn't it? The first process, the process 2-3, and the another process during which the heat is added is nothing but the process 4-5, isn't it? So we are writing here Q combustor. So it means that the heat which is supplied there in the combustion chamber during the process 2-3, and the Q reheater, so that is the heat which is supplied in the reheater, so that is the process 4 to 5. And if we write down this equation for the thermal efficiency in terms of the temperatures at different salient points, okay, so Cp into T3 minus T4. Cp is nothing but the specific heat. T3, temperature of the gases at the inlet of high pressure turbine. T4, temperature of the gases which is leaving the high pressure turbine. Okay, so this is nothing but the work which is obtained from the high pressure turbine, that is Cp into T3 minus T4. Then we add Cp into T5 minus T6, which is nothing but the work obtained from the low pressure turbine. So T5, temperature of the gases after reheating and entering the low pressure turbine. T6, temperature of the gases leaving the low pressure turbine. Okay, so Cp into T3 minus T4 plus Cp into T5 minus T6. So this indeed is nothing but the work obtained from high pressure turbine and the low pressure turbine. And we subtract the work for the compressor. So Cp into T2 minus T1. So T2 is nothing but the temperature after the compression for the air, and T1 is nothing but the temperature of the inlet air that is entering into the compressor at point 1. Okay, so this entire numerator that gives us the net work obtained from the cycle. Coming there onto the denominator side, Cp into T3 minus T2. T3 is nothing but the temperature after the heat addition. One can also see that the temperature T3 is nothing but the T max, the maximum temperature in the cycle, isn't it? If we see it, the point 3, so the temperature T3, that is nothing but the maximum temperature which can be seen in the reheat cycle. Okay, so Cp into T3 minus T2. T3, temperature after the reheat. Temperature T2, that is the temperature before the T3 is nothing but the temperature after heating rather, not the reheat. I will say it is the temperature after the heating in the combustion chamber, and T2 is nothing but the temperature of the air that is entering into the combustion chamber. Then this plus Cp into T5 minus T4. Okay, so 4 to 5 is nothing but the reheat process. So T5, temperature after reheating, and temperature T4 is nothing but the temperature before reheating. So Cp into T5 minus T4. So that is the heat which is supplied in the reheater. So by this equation, it is possible for us to evaluate, to determine the thermal efficiency of the reheat cycle. Okay, so I hope that you have understood the arrangement for this reheat cycle. Okay, consisting of high pressure and low pressure turbine, and you place the reheater in between the both these turbines. And I mentioned earlier that this cycle does not reduce the work required for the compression, but it in turn increases the net work which can be obtained from the cycle. Hence, the thermal efficiency of the cycle increases. Okay, so we stop here for this arrangement for the reheating. The another arrangement that is used for improving the thermal efficiency of gas turbine power plant, so that is the regeneration. We will discuss that regeneration arrangement in the next lecture. Thank you very much.